This presentation provides an overview of the Stream Quantification Tool, which is an application of the Stream Functions Pyramid framework. So the Stream Functions Pyramid and the framework concept is not reviewed on this presentation, but people can view another webinar or just the information that's on the Stream Mechanics webpage for more information on the Stream Functions Pyramid and the framework. So the primary purpose of the Stream Quantification Tool, there are really 5 purposes of the SQT, the Stream Quantification Tool. The first and most important, the primary reason the Stream Quantification Tool was developed was to determine numerical differences between an existing stream condition and a proposed stream condition, as well as the monitored condition. So existing would be the degraded state of the stream, and then the proposed would be determined during the stream restoration planning process and design process, if it's a mitigation project during that mitigation plan, and then the monitoring years would provide the stream condition for that time so that we can compare functional lift between that existing condition and the after condition. And then the second is to link the restoration activities to changes in stream functions, which we describe those stream functions with function-based parameters. That's a term from the Stream Functions Pyramid framework, and they are provided by a functional category. So hydrology, hydraulics, geomorphology, physicochemical, and biology. And one of the things that makes this assessment unique is that a lot of care was taken to pick metrics that can be manipulated by stream restoration activities in order to determine a difference, you know, if it's a restoration project, in order to see that lift. And then third is to link the restoration goals to restoration potential. So this idea, function-based goals, restoration potential, is also described in more detail as part of the Stream Functions Pyramid framework. And it's not a quantitative part of the SQT, but there is a place in the worksheet, in the spreadsheet, for people to list their function-based goals and to describe the restoration potential and to make sure that there's a match. In other words, that people are not articulating goals that are not supported by the restoration potential. For example, goals that may state that the biology will be returned to a reference condition, and yet the restoration potential is not that high. The restoration potential is more about stability or habitat because of the stressors and perturbations in the watershed. And then 4, to incentivize high quality stream mitigation. In other words, the more lift that people get, the more credit they would get. And so the tool is designed to do that. The more benefit that there is for a project, the more credit that there will be. And then finally, to assist with site selection. So since the tool will provide idea of lift, then users can quickly run the tool during a recon or prospectus stage of a project to see if there is enough lift to warrant a project. So this is just a sort of a schematic or picture view Venn diagram that's kind of saying the same thing as part of the other slide. So we have restoration activities at the top. This just acknowledges that the stream restoration field requires people to go out into the field and do something, whether it's planting trees, that would be sort of a minimal activity, or building a new channel, which would be a more intense effort. But regardless, there will be some type of activity that's done on the landscape with the idea of seeing a benefit and then hopefully getting credits. And so that benefit is the functional lift component. We want the after function to be higher than the before function. And then finally, we're acknowledging that restoration requires money to do the work, whether it's mitigation or not. People are are applying funds in order to get a result. So we wanted the SQT to live in a world between these three things, acknowledging that there are restoration activities, that we want to produce lift, and that if it's in a mitigation, the SQT was primarily built with metrics from single thread channels, perennial and intermittent stream flow. However, some tools like the Tennessee SQT includes an ephemeral component as well. The tool itself doesn't care. In fact, it's best to think of the stream quantification tool as a calculator of functional lift using existing stream assessment methods. So quite a few different methods are used, and then they are plugged into the SQT to calculate lift or loss. And then I'll talk about reference standards in a minute, but the scoring is compared against reference standards. So as long as that data comes from perennial, intermittent, and ephemeral, then the tool will apply to those settings. But right now, more tools have more data in the perennial and intermittent camps than the ephemeral camps. So there are a number of resources that are available for folks to use. I'll skip to the bottom first. I mean, all of this information is on the Stream Mechanics webpage under the Pyramid Framework tab. But going back to the top here, there are user manuals, the SQT. The user manuals do vary a bit by state, by the states that are using the SQT. They put their own flavor to developing these manuals. But in one way or another, the manuals describe how to use the spreadsheet, the Stream Quantification Tool spreadsheet, and then there are data collection user manuals, both providing rapid methods to collect data, as well as what we call more detailed methods of collecting the data. The rapid data collection methods are ways that we can collect primarily the hydrology, hydraulic, and geomorphology data without using surveying equipment. And then the detailed methods are a more thorough description of measuring those parameters, typically using surveying methods, whether it's a standard level or a total station. And then the final resource is the science support and rationale document. So this really gets into why, or the how and the why, the reference standards were developed. And for now, there is a science support document for Wyoming, and then the other states are being developed. So click on the Stream Mechanics webpage and go under the Pyramid Framework, and you can see what science support documents and other user manuals are available. There are also spreadsheets that go with that are available. So the primary spreadsheet is the Stream Quantification Tool. So that's the spreadsheet that's calculating the functional change, which is the existing, the proposed, and the monitoring years. There's also a debit tool component, and that is used for the permitted impacts to estimate functional loss. You could actually use the SQT, the Stream Quantification Tool, to calculate loss. It will do that. The challenge on the permitted impact side is that we do not monitor impacts after they have occurred. So the debit tool provides a way to predict those impacts, recognizing that they will not be monitored. But it gives you the same currency. So the units for the debit tool match the units for the SQT. So for those people that want to use the SQT and debit tool for doing debit and credit determinations, it provides a way to do that. And then we also provide examples of the SQT and the debit tool, so you can see what these spreadsheets look like when they're completed. They have data in them. There's a list of metrics spreadsheet that's kind of like the science support document light. It's not a narrative. It doesn't give you the rationale behind the reference curves, but it is a quick look at all of the parameters, all of the measurement methods, and then the reference standards, and the way those measurement methods and references are stratified, and then the references that we use to develop those reference curves. So it's a quick look at again, just the comprehensive list of metrics and the reference curves and where they came from. So I mentioned this, that the SQT is an Excel workbook. It has multiple worksheets, and again, this varies slightly by state and by SQT as different regions, different states take the SQT and regionalize it for their use. But the standard format is this, where we have a project assessment worksheet. This is a place where people can articulate their function-based goals and objectives, put a reach scale map. There's also the place on this spreadsheet for credits and contact if you find a problem and so on. The next worksheet is the catchment assessment sheet. So this is, I'm not going to get into a lot of detail with this, but the catchment assessment allows the user to identify the stressors and the perturbations that are occurring in the watershed. So outside of their control, outside of the reach that will be part of the project, that's within a conservation easement, for example. The catchment assessment is a quick, fairly rapid look at all of those things that are happening beyond your project reach that could limit your restoration potential. So while we did try to pick metrics within the SQT that are reach scale and can be changed by a practitioner, we did not want to ignore the fact that there's a lot of other things happening in the watershed that can affect our project. So this is the place to do that. The next spreadsheet or worksheet is the parameter selection guide. So this tells the user what parameters are required to be assessed for every project and which parameters could be selected based on a condition. So based on the environment, for example. To give an example, large woody debris is a parameter in the SQT, but it would not be required in all tools for all places because some SQTs are in deserts or plain environments, and maybe large woody debris is not needed for those areas. But for places like North Carolina or Tennessee where the whole state is wooded, then it would more likely be required. So the quantification tool is the kind of the heart and soul of the workbook. This is where the lift and the loss calculations take place. The reference standards worksheet is a big worksheet with all the different reference curves where if we know what the field value is, it will return an index value. This is where the scoring happens. There's a worksheet for the monitoring data. It's a place where people can enter up to 10 years worth of monitoring information. And then the data summary worksheet graphs and puts that monitoring data into a table format. And then I mentioned the debit tool. It is built into some SQTs, and it's a separate spreadsheet file, a separate workbook for other SQTs. Okay, so to spend a little bit of time on the stream quantification tool worksheet, this is one of the first things that the user will see in the upper left part of the worksheet is this table. And this is a very important table because this is a place for people to put their reach information and to determine this, what we call stratifications. So project name, folks can just type in, reach ID, they can type in. For other things like existing stream type, proposed stream type, ecoregion, these are drop-down menus, and people should use the drop-down menu instead of typing it in. The spreadsheet will use this information to tell the tool which reference curve to use. So for example, many reference curves are stratified by the information here. So let's take ecoregion as an example. We may have macroinvertebrate data, performance curves, but we know that in North Carolina, for example, macroinvertebrate communities in the mountains are different than macroinvertebrate communities in the coastal plain. So we would use this ecoregion, sometimes we use physiographic region to make that stratification. So if we picked mountains here for North Carolina, we just told the tool that when we have data for macroinvertebrates, use the mountain curve. and so on. Drainage area is a way to stratify. Bed material, proposed flow type, perennial, intermittent, ephemeral. These are all stratifiers, and it's best to just fill out this entire table, because when you're entering data into the existing or proposed condition and the tool returns a false, it typically means that the user did not complete this reach information and reference standard stratification. So I recommend you just fill out the complete table whether you need it or not, and that way you know you're covered. Okay, so when you scroll down from that, you'll see an existing condition assessment table. Underneath that, there's an identical table for the proposed condition assessment, and then the user would just add the field value, which is the column in gray, and the tool will return the index value. And you'll see you see that this table is organized by the stream functions pyramid, where you have the functional categories, the function-based parameters, the measurement methods, and then you enter your field value. You do not have to enter a value for every single measurement method. In other words, if you do not enter a value for a measurement method in the field value column, it's simply removed from the tool. It does not create a zero, or it does not hurt your scoring by not having data. So here's the scoring range. We put everything on a 0 to 1 scale. We did keep these 3 buckets of not functioning, functioning at risk, and functioning from the stream functions pyramid framework, just as a way to frame and provide meaning to these numbers. Not functioning is from 0 to 0.29, and then once we hit 0.3, we've moved into the functioning at risk category. And then when we hit 0.7, we move into the functioning category. There is a reference standards worksheet then that's related to this scoring. So the way this works is the user enters in that field value, which you see here on the x-axis. This is a reference standard for pool depth ratio, which is the depth of the pool, the max depth of the pool, divided by the mean depth of the riffle. So you could think of it as how many times deeper is the pool than the riffle. The y-axis here is the index value, and there are these regression equations fit to 2 lines that go from a 0 index score up to 0.7, which is functioning. That's the beginning of the functioning range. And then another regression line that goes from the beginning of functioning up to a 1.0, which would essentially be like a pristine condition. Although 0.721 all represents reference condition. And so a couple of things to note here. One is that with these regression lines, you have better resolution in this tool than tools that just have buckets of like not functioning, functioning at risk, and functioning. You would have to change all the way from not functioning to functioning at risk without this tool to see a change. And there's a lot more lift if you went from really not functioning to the high end of functioning at risk versus if you were almost functioning at risk and went to just barely functioning at risk. So that's one reason that these categorical buckets are not as effective for showing lift as having equations like this. You can also see that the field value of 1, so if the ratio, the pool is basically the same depth as the riffle, there is no functional value. It really wouldn't be a pool if the pool wasn't deeper than the riffle. And so as that ratio increases, we're increasing the index value. And then when you get to 0.7 into the functioning range, that rate of improvement goes down. You're functioning as your pool gets deeper. There's still some functional value to that, and then it caps out at a ratio of about 3.2 or so. So anything over 3.2 would still yield an index value of 1.0. Okay, so here's the scoring. So it's a very simple scoring method. It's simply, for the most part, an averaging tool. We take the measurement method index scores we average them together to get a parameter score. We take the parameter scores, average them together to get functional category scores. And then we have a little bit of a twist. So there are 5 functional categories. Each functional category score is multiplied by 0.2 and then summed to create an overall score. So if someone only measured through level 3 geomorphology, their max score would be 0.6. If they measured through level 4 physicochemical, their max score could be 0.8. And if they measured through biology, their max score could be 1.0. Usually at this point, people will ask the question about weighting and why didn't we weight? And it's a fairly long answer. The short answer to that is to provide the flexibility of the tool. We wanted to focus on lift, the delta between the existing and the proposed condition, and we wanted to make the tool flexible enough that we could have required parameters and optional parameters. It would be very difficult to do that if you had weighting for each parameter. Plus, how do you do that weighting? I mean, the best way to do it is with some form of statistical analysis, which could take years to develop. And then again, once you do, you lose your flexibility. In the absence of that, and just using best professional judgment to do it, you enter this area of kind of people thinking it's a black box, and we've actually seen some assessment methods get thrown out because people didn't understand how they came up with that weighting. So we just decided to not do that and make the math very simple and keep the architecture of the tool very flexible. It's not to say that in the future at some point we won't add weighting, but I do think we're years away from doing that. Okay, so how is functional lift calculated? It's very simple, and it's based on historical methods for doing functional lift within stream mitigation programs, where we take the quantity, so we are still using stream lengths in the form of stream feet, and we're multiplying it by a condition score, which you could think of as a % of function. It's that scale that we just showed. So the product of those two is what we call functional feet. And so then functional lift is the delta, or the change in functional feet. So what we're really focused on is that proposed functional foot score minus the existing functional foot score. And there are a few basic rules that we try to follow, not trying to get into policy, but just to make the tool work the way that it's supposed to. It is important that the same parameters evaluated on the existing side are also evaluated on the proposed side, and that you must include certain parameters, and that those parameters that must always be included are in the parameter selection guide. This is here to prevent gamesmanship, so that people don't pick just the parameters that will give them the worst score on the existing side and the best score on the proposed side, and ignore metrics that might be important to characterize the condition of the stream, but that they don't want to measure because they don't think they'll have a change. So again, this is here to prevent that gamesmanship. And then we do recommend adding parameters based on specific scenarios and environments. So as we get into the results, there's a couple of ways to look at the results, and there's a table in the stream quantification tool that shows this. So there's an existing condition score, the ECS, the proposed condition score, and then there's that first measure of lift, which is the condition lift. That's the PCS minus the ECS. These are those index values that have been averaged, like I was just showing. It is irrespective of length. Length is not part of this condition lift. The functional feet incorporates the length. So we now have our existing functional foot or functional feet, which is the existing stream length times the existing condition score. We have our proposed functional feet, which is the proposed stream length times the proposed condition score. And then our lift is just the proposed functional feet minus the existing functional feet. So this does require people to think a little bit differently than they have before, especially in the mitigation world, because the vast majority of mitigation crediting is simply about an end result. If you change dimension, pattern, and profile, you will get restoration credit, for example. Lift has typically not been part of the math. And so I put this graph here just to begin to give a visual of what this tool is doing, where we're focused on. We are focused on the lift, but there does need to be a minimum quality obtained. That's why we have required parameters. You can't just go to a site and say, I'm just going to plant trees and capture whatever lift is obtained by planting trees. Like, there's a minimum amount of lift or a minimum quality that must be achieved. But once that minimum is achieved, the focus is on the lift, not on where you end up. So in this graph, for example, you can see that you started with a really bad stream, and this is assuming you're measuring through all 5 levels. So you started, your stream was just trashed. It had a not functioning score of 0.1. You came in, you did some restoration activities, and you lifted it so your overall score was 0.5. Well, that's a lot of lift. Your delta here on a condition score is 0.4. But your overall quality is still middle of the road, functioning at risk. That is okay. It doesn't mean you don't get your credits because your stream is functioning at risk. You took a dead stream and you brought some habitat, maybe even some biological life back. You just didn't take it to reference condition. But that 0.4 is a lot of lift, and credit would be given for that. You might think of that as an urban project. We're seeing urban projects actually generate quite a bit of lift. Now, on this side, you can see you started with a 0.6. And so this would be a stream that was pretty good before you started. It was not in horrible shape. It was the upper end of functioning at risk, and you lifted it to 0.8, which is a highly functional stream. Reference condition, almost pristine. 1.0 would be your culturally unaltered or pristine condition. So very high quality, but a low lift. You only went up 0.2 units with the work that you did. So this project, even though it has a higher quality than the last project, would produce less credit, less lift, less mitigation credit. So you might think of this as a rural project that has a little bit of problem, but it's downstream of a really good watershed. So here's a picture example of what we're talking about. So here's an existing condition stream, existing condition score of 0.19, existing stream length of 972 feet. So your functional foot is 185 functional feet. The proposed condition would be, proposed condition is the condition that is expected to be seen at the end of monitoring. So for this project, 5 years of monitoring. This is only measuring through level 3 geomorphology. We are not measuring physicochemical or biology. Therefore, no lift can be captured in physicochemical or biology. Proposed condition score 0.35, proposed stream length of 1280. So the proposed functional foot is 448. So the lift is 448 minus 185. This could be 263 functional feet. It could also be 263 credits as long as the debit method followed the SQT as well. In other words, you can't take this 263 functional feet and call it credits in a ratio-based method where on the debit side it was just 1 credit or two credits needed per foot, for example. We're not going to mix units. So 263 credits required if the debit method used the SQT or debit tool as well. The important point here, though, is that this lift does fit the definition of a credit. The results also give a functional lift summary table. So for that site, you can see the existing condition score, the proposed condition score. I like to focus on this first functional lift score, that 0.16. That means we had 84% lift of quality lift from the existing to the proposed. We also added stream length to this project. There was 308 more stream length after the project than before. And so if we look at the proposed functional foot minus the existing functional foot, it's 263. The functional lift is higher at 143% because that extra lift was provided, or that extra length was included. So there is an incentive in the SQT to include stream length. However, sinuosity is one of the function-based parameters, and it's a curve, meaning too little sinuosity is bad and too high of sinuosity is bad as well. And of course, that is stratified by stream type. So here's another output of the tool. I like this type of output where you can see which parameters were assessed, both for the existing and the proposed. It's a place to do a little bit of quality control to make sure that all of the proposed parameters were the same parameters assessed on the existing condition. And then you can quickly see that where there was lift and where there was not. So red is not functioning, yellow is functioning at risk, and green is functioning. Give the same kind of information by functional category. So again, physical, chemical, and biology functional categories were not assessed. And then here's the monitoring results. So there's a table that just allows people to put up to, I said up to 10 years. It's actually up to 10 monitoring events. So if you did them 10 consecutive years, that would be fine. But you can see here, there's the existing parameter column, proposed, as-built, and then there were monitoring years 1, 2, 3, 4, 5, and then year 13. And so again, by parameter, you can see where there was change and where there was not. So there were no changes in hydrology. This is an older SQT that included catchment hydrology, which was one exception to a reach scale parameter. We are phasing this parameter out in many of the tools and focusing more on the reach runoff parameter. Again, this was an opportunity lost. This is an old project, and so there was no mechanism to deal with lateral runoff, reach runoff, and so you see it wasn't good. There was a pipe bringing water right into the reach. It was there before, it was there after, and so no change throughout the life of that project. Other parameters like floodplain connectivity, you can see it was changed, and then it just stayed the same throughout those monitoring years. Whereas things like riparian vegetation, you can see the as-built is not as good as the proposed, but over time, that parameter is getting better and better. So if we look down at the very last row, you see the existing condition, functional foot was 185, proposed was 448, as-built was less than that at 435. That will be common, but then by year 5, we hit the 448. And what's encouraging is we went back in year 13 to see how the site was doing, and it was actually getting better, 461. So you could use the tool to basically measure channel evolution, channel change over time. And fortunately here, the trajectory is still up. And then there's just a graph that shows that same data. So you can see what is that, sort of a pink line for the existing condition. And then the gray dashed line for the as-built, blue for proposed, and the black for monitoring. So you see in that year 0 or year 1, the monitoring is below the as-built. The as-built is below the proposed, but by year 5, they all converge, so that now the monitoring equals the proposed is better than the as-built. And if we come over to year 13, we see that upward trend. The monitoring is still better than the proposed and the as-built, and of course the existing condition as well. Okay, so just to wrap things up, this is the current regionalization schedule. The North Carolina tool was the first. It is now fairly outdated, and we're hoping to update that this year, 2018, going into 2019. South Carolina is regionalizing the SQT. Georgia has a SQT Lite. They only have a few parameters that have been regionalized to date. Tennessee is done. Michigan is in progress. Wyoming is done. Colorado and Minnesota both are in progress. So as these are completed, they'll be put on the Stream Mechanics webpage. So just check that webpage frequently to see what SQTs are completed and which ones are not. And thank you very much for your time. Check our webpage for updates, or feel free to send an email or call. That information is on the webpage if you have any questions. Thank you.